on to the first speaker. And as I said, this gentleman is really one of my favorites. I've heard him speak now, I don't know if I'd be exaggerating if I'd said 10 times, probably 10 times at least. I've learned something new each and every time. He has a real commanding presence live, and I'm assuming that commanding presence probably translates over to this virtual event as well. There's just something about his voice that just soothes me, and I really focus in and I learn something new each and every time. And I can hear him now talking about the current flow doesn't actually flow through the traces, but it flows in the space between the traces and between the layers of the board. And he's just an excellent presenter. He's also one of those gentlemen that we're quite proud to be associated with because of his legendary status. And without further sort of delay, we'd like to bring in Rick Hartley.
Rick Hartley, retired from L3 Avionics, is the principal engineer of R. Hartley Enterprises, through which he consults and teaches internationally to resolve EMI, noise, and signal integrity issues. He's helped major corporations in the US and 14 other countries. Rick's 50 years in industry is focused on circuit and PC board design for computers, aircraft avionics, and telecommunications. His consulting focuses on those industries as well as medical systems, automotive electronics, and appliances. Rick has an engineering degree and 55 years in electronics engineering. He's taught seminars at various IEEE events, PCB West, Freescale Technology Forum, AltiumLive, IPC Apex Expo, and other public and private forums. Rick is a member of the IEEE, the Executive Board of PCEA, and a past member of the Editorial Review Board of Printed Circuit Design magazine. Additionally, he's written numerous technical papers and articles on methods to control noise, EMI, and signal integrity. Please welcome Rick Hartley.
Hello, everybody. Thank you for attending, and thank you for that very nice introduction. PC board optimization, meaning what? There's a lot of things you could optimize on a PC board. In this particular case, we're going to talk about designing boards to optimize manufacturability. Mostly we're going to discuss fabrication, but to a small degree, we will also discuss assembly. When I was putting the material together for this, it occurred to me that I could make a really long presentation out of this. I could easily make 4 to 6, maybe even 8 hours of material on this topic, and I might very well do that in the future. But for today, we have an hour and a half, and we've got a lot of ground to cover, and that hour and a half includes Q&A. So let's get started. Bareboard fabricators, when you send a circuit board, a design, to a bareboard fabricator, they have a list of critical parameters that they look at, and they review those parameters relative to your design to decide just how producible your board is. And here's a list of some of those parameters. Board size versus number that will fit into a panel is, notice that's item number 1 on the list. That's one of the key items that fabricators will look at when they're reviewing your design. Why? Because how much material they have to use to build your boards will have a big impact on what they're going to charge you and what it's going to take for them to give you a reasonable price and still have a profit margin for themselves. We're going to talk in a few minutes about what I mean by a panel. For those of you who aren't familiar with the term, circuit board fabricators don't build boards one at a time. They build panels, and I'll go through more of that in a moment. Another of the parameters they look very hard at is material of construction. What is it made of? Chem 3, FR4, polyimide, whatever. Each of them has a different weighted cost, and you'll see what I mean on that in just a moment as well. Number of layers. Clearly, everybody listening to this knows that number of layers plays a role. A 2-layer board is going to be cheaper than a 4, cheaper than a 6, and so on and so on. But not just layers, but layers per given board thickness. I've met far too many engineers in my life and board designers who somehow think it's okay to put 16 or 18 layers in a 62 mil thick, 1.6 millimeter thick circuit board. I'm not sure where the concept even came from. Well, I do know where the concept came from. A lot of engineers think, and especially mechanical people, that circuit boards always need to be a 1/16 of an inch thick. That's been a long held belief, because in the early days of circuit board design and fabrication, the materials they used that they started with early on just happened to be a 1/16 of an inch thick. That was simply what they used. There were many reasons for that. Not going to get into that today, but they started with 1/16 material, and the early 1 and 2 layer boards were laminated, were fabricated on 62 mil thick material. That concept has kind of stuck with everybody. And to make matters worse, a lot of people put boards in card guides that plug into a backplane. And a lot of the card guides have 62 mil slots in them, or 70 mil slots, forcing you to put a 62 mil thick board in there. And that's all fine and dandy, but you really have to think about the art of the possible. When you put 16 layers into a 62 mil thick board, the dielectrics are painfully thin, and it makes the fabricator's job much harder than you think it is, or would be, especially if it's a controlled impedance design. Controlled impedance boards require much greater care and much more control of dielectrics than the thin dielectrics you'll end up with putting 16 or 18 layers in a 62 mil thick board. When I was at L3, for example, L3 Avionics Systems, I don't know that all L3 divisions do this, but ours did. We did a lot of 12-layer boards, and we worked with our fabricator to come up with an optimum board thickness for 12 layers. And we collectively, working with them, arrived at a 75 mil plus or minus 5 mil thickness for our 12-layer boards. That gave us dielectrics that were easy for them to control, and allowed us to use line widths that gave us good routing densities and still hit the target impedance we were after. All of these issues played together. We could have put 12 layers in 62 mils, but it would have changed things to the point where it would have made the fabricator's job more challenging, because a 50 ohm line would have been a narrower trace. And narrower traces are harder to hit with controlled impedance. It's just that simple. So the point I'm making is, think carefully about what you're doing when you choose a board thickness. Drive into the mechanical people's heads, pardon me, drive into the mechanical people's heads. The boards aren't all 62 mils thick. If you're going to mount boards on 4 screws on standoffs, or 8 screws or whatever, they certainly don't have to be a defined thickness. They can be whatever you need for them to be. Make sure everybody's aware of that and work with that. Number of holes in a panel. They used to charge per hole. They don't do that anymore. But you still pay based on lots of holes. Up to 3,000 is a fixed cost, typically per panel. 3,000 to 10,000 is a little bit higher cost in a panel, and so on. There are groups that there are quantities that they group together, and when you step up in mass quantity of holes, price is going to go up. I mean, it just takes longer to drill and wears out more drill bits. It's that simple. Smallest hole diameter. What's the smallest hole they can put into a board based on your thickness and still get the drill to go through the board straight without wandering, and be able to wash plating solution through that hole and get an even plating all the way through the hole when they get to the plating process. There is a minimum size, and it's not just a minimum size, it's a minimum size based on board thickness. There are aspect ratios that they can hit. The aspect ratio for a 62 mil thick board might be different than the aspect ratio for a 93 mil or a 120 mil thick board. 6:1 aspect ratio is something that in most boards, most fabricators can hit. Asking for 6:1 aspect ratio in a 62 mil board is relatively easy. 10:1 aspect ratio is another one that most of them can hit, but it certainly is going to be a cost header. You will pay more for a 10:1 aspect ratio than you will a 6:1. Can they do 10:1 in a 62 mil board? Most fabricators can't, because that would be a 6 mil plated hole. They would have to drill a 7 to 7.5 mil hole and plate it back to 6 mils. very challenging for a fabricator to do. Talk to the fabricators, know what you can do. We'll talk more about that as we go. Pad to hole ratio, there are pad to hole ratios that are set by not only the fabricators, but by the IPC standards. Most fabricators follow the IPC standards as the guideline for producing circuit boards. If you're not familiar with IPC standards, you really need to become familiar with them. IPC 2200 series, 2221, 2222, and so on. The 6000 series, 6011, 6012. If you're doing flex, 6013. The manufacturing series, 610, 611, and there are plenty of others. Those are just examples of standards you, as a designer or an engineer, if you're designing circuit boards, need to be familiar with. So keep all that in mind. If your company's not an IPC member, try to get them to be. If not, then just buy the standards directly from IPC. You'll pay more if you're not an IPC member, but they're still very reasonably priced. I mean, anywhere from $20 to $50 each, and that's not outrageous, given that you probably only need a half dozen or so. So think about that very carefully. Anyway, all of these things that you see here, hole to board thickness, aspect ratio, we talked about, all of these things matter. Here are some additional items to consider, and these are things the fabricator looks at in your design. Minimum trace width and space. What is the minimum trace and space that you can put on and in the board? And oh, by the way, you can put narrower traces inside of a board than you can on the surface of the board. Why? Because inner layers are printed and etched. Outer layers are printed, plated, and etched, and it makes a difference just exactly what line width you can produce on and in a circuit board. We will cover some of that later. Trace space width versus copper thickness. We're going to talk about that later. Why would that matter? Because if copper is 2.5 or 3 mils thick on an outer layer, do you honestly think you could etch a 3 mil line in copper that's 3.5 mils thick? It's no longer going to be a rectangle, it's going to be a square when you look at it in cross section. And that's going to be a real challenge for a fabricator to do. They might be able to do it, but the scrap rate's going to go up. Speaking of which, when there's scrap at a fab house, who do you think pays for that? If you've guessed us as the designers, our companies, you're right. You've guessed correctly. Fabricators know their processes and know them well. And if we ship them designs that make sense, that are well thought out, they won't have scrap, or they'll have so little it'll be almost irrelevant. When they have high levels of scrap, it's because I and others like me, have not done our job properly. Scrap is our problem, and guess what? We pay for it. And we'll talk more about that in a few minutes. Design specific features, there are a lot of, controlled impedance. Do you need controlled impedance? You're going to pay more for that. What tolerance do you need? We'll talk about that in 1 second. The source for these bullet items that we're looking at is a paper from our friend Happy Holden, and you can find it on Altium's website, altium.com. All you have to do is look up Design Report Card by Happy Holden, and you will find this. You will also find in that paper this particular table. This is an example of a fabricator's report card, and you can see the line items on here. Material of construction. Notice these are weighting factors. You want low numbers on your report card, because the lower number your fabricator comes up with on the report card, the less they're going to charge you per panel. They determine a cost per panel based on the score that they create when they establish a report card for you. Higher scores means you're going to pay more per panel. Lower score means you're going to pay less per panel. Notice that FR4 has a score that's 1/3 that of polyimide. Do you need polyimide? Well, unless you do, I certainly wouldn't specify it, unless you truly need it for temperature reasons, which is typically why people would spec it. Obviously, polyimide is classically used in flex boards, and there are many reasons for that, but I'm talking about rigid boards in this case. If you need something that's really high end, like a Rogers Taconic or Arlon material, or one of the high end Isola or Nelco materials, or something from Matsushita, who's Panasonic, or any number of other companies. There are a lot of companies that make high end materials. If you need these high end materials, then you have to specify them. But understand they do have a cost weight associated with them. Number of holes in the panel, number of layers per panel, max trace space, and so on. All of these things, look at this table, they all have a weighting factor. And that factor will determine what you're going to pay for that board. Very important to understand the impact these things have. Read this paper by Happy. You will learn a lot. And we're going to talk about some of these items today. PC board fabricators don't build boards, they build panels of boards. And they cut the boards out of the panel at the end so that you won't have the aggravation of having to do it. The reality is, until that very last step where they excise the boards from the panel, everything is done in a panel. What you pay for each board is a function of how many panels they have to run to build your lot of boards. As an example, if you order 100 boards from a fabricator and they're able to fit 10 boards in a panel, and they're able to produce only 10 panels to produce your 100 boards because they're really confident they're not going to have any scrap, then you'll get charged for 10 panels. If they think that your board isn't that well designed and they need to make 10 extra, 5 or 10 extra, and they would just make 10 extra, they wouldn't make 5 extra in that case, they will run an extra panel. They'll run 11 panels. If your board or my board or whatever is so poorly designed that they need to run 12 panels because they're really not confident about the ability to build it without fallout, without scrap, then we're going to pay for 12 panels. Nothing's free in this world. The number of panels they run is what you will pay for the boards, and they will divide the number of boards into the number of panels, and that's where the price per board comes from. And remember, the weighting factor for each panel is a function of how well you do on the report card. Keep that in mind. Something that is common at every board house on planet Earth is an 18 by 24 inch panel. Now, it's still thought of in most parts of the world as an 18 inch by 24 inch, even though the lion's share of the world is metric, because it started out that way. And to this day, they still produce material at laminate suppliers in 3 foot by 4 foot sheets. When the fab house receives the laminate, the 3 by 4 sheets, they will cut it into 4 equally sized panels of 18 by 24 inches. And they build boards in those 18 by 24 panels. Well, what if you've got a small board and you don't need a whole panel? They can build sub-panels. They'll build a half panel. They'll build a 12 by 18 panel, for example, because that will still fit in all their machinery. Their machinery is sized in the early days, not so much now, but was sized in the early days for a maximum panel size of 18 by 24. And that's where this came from. All the equipment they bought, the drill machines, the plating line, the image line, the etching line, everything was sized around an 18 by 24 panel. They can run smaller panels, and often do. They can even run a 9 by 12 if they need to really only build 1 or 2 medium-sized boards or several very small boards. This is something they can do easily. In the 1970s, a bus style called the VME bus came along. I was in the industrial controls world in the 1970s and the first half of the 80s, and we put equipment on factory floors that was in large cabinets, single and double bay cabinets, and sometimes in pizza boxes, but usually in larger cabinets. And these cabinets would talk back and forth to each other, and all the exchange of data that took place in the cabinets was done using a bus called the VME bus. It was a very wide bus. I don't remember if it was 64, 128, or maybe even 256 bits, but it was a wide bus, really wide. And the line cards that plugged into the back planes for the VME bus were a brilliantly sized circuit board. The people that designed them really, really, really thought about their size. And they knew that if they sized them correctly, they would fit perfectly in a sub panel of circuit board material, and there'd be almost no scrap. They made the circuit boards between 14 and a half to 15 by somewhere around 16. They were ballpark in that vicinity. That was roughly the size they were. Fabricators soon realized that if they cut a 3 by 4 foot sheet into 6 panels, they would get 16 by 18 sub panels, which they could also run on their 18 by 24 sized equipment. And they could fit one VME board perfectly into that 16 by 18 panel with so little scrap that almost nothing got thrown away. I mean, this was brilliantly done. Unfortunately, there was another company at the same time who designed a board that became very popular, and a company called IBM. I'm sure many of you have heard of these guys. They're the ones who came out with the initial personal computer. The first version of the PC was an XT design. It was called the XT computer. And the motherboard for the XT was sized at 12 inches by 13.8 inches. Well, I'm going to show you in a minute why this is true, but that board size panelized terribly. I mean, terribly in everything that fabricators had that they could produce. The closest they could get to getting reasonable production with the 12 by 13.8 motherboard was in a 16 by 18 panel that we're talking about. Well, for the first few years, the first few months to a year or so that the PC existed, everybody who bought them, whether it was IBM or the clone manufacturers that were making other versions of that same design, anybody who bought a motherboard paid too much for the motherboard because they didn't panelize well in these panels. And the majority of the material from the panel got tossed into the trash. And you pay for what they use, not for the board you buy. You don't pay for a board based on its size. You pay for a board based on how many panels they have to run to produce the number you request. It's as simple as that. It all comes down to what they have to use to make your design. And IBM's motherboard was a terrible size. And again, we'll talk about why in a moment. The only thing that was good in IBM's favor back then was the fact that at some point the PC took off. I mean, like a shot, the PC took off and became such a popular item, as everybody, of course, knows, that they went from making a few hundred per week to a few hundred per day to a few thousand per day to a few tens of thousands per day. And all of a sudden, the people producing motherboards said, you know, there's a big market here. And there's a real opportunity to make some big money in this market, but we're never going to be able to do it running 18 by 24 panels. That just isn't going to work. So they contacted the equipment suppliers and they said, hey, equipment suppliers, can you make etching lines, plating lines, drill machines, imaging equipment, all this equipment? Can you make these lines and baths so that we can put larger than 18 by 24 panels in them? Can you make them so we can put panels of 21 by 24, 18 by 26, 21 by 26, and even other sizes beyond that? These are just samples, examples of sizes that fabricators requested. And why did they do this? So that they could cost effectively produce the XT motherboard. And it wasn't just the motherboard. There were plug-in boards. There were periphery boards that plugged into the motherboard, originally called XT plugins, and then eventually the AT and the AT plugins. The AT and XT plug-in boards were approximately the same size as one another, and they too did not panelize well in 18 by 24 or even 16 by 18 panels. The IBM, the point I'm making is the IBM engineers either were clueless or naive or arrogant. And I'm not sure which it was, but when they chose the motherboard, they clearly didn't do it with manufacturing in mind. They were either so arrogant they didn't care and honestly believed they were going to rule the world and the world would change to meet them, which is what happened, by the way. The world ended up changing to meet the demands of the PC market. And eventually, fabricators all over the world started producing other panel sizes. The point I'm making here is simple. You have a list of fabricators that your company uses. They may be buying boards through their contract manufacturer. They may be buying boards through your purchasing people directly. However it's done, you have a list of suppliers that you use. And I can guarantee that your suppliers don't all use the same panel sizes. They will use some of the panels that you see here, and they might even use other panel sizes that aren't here. Before you design your next project, you should find out all of the panels that all of your suppliers can produce with, and pick a panel size or panel sizes that is common to all of your suppliers, so that you can pick board sizes, and I'm going to tell you in a minute how to do this, that panelize well for producibility. If you want to minimize cost and minimize scrap and minimize what you pay for boards, don't choose the cheap vendor. That's not the solution. That's what purchasing does. They choose the cheap vendor because they don't have the knowledge to do otherwise. Work with the fabricators, get to know their processes, and use panel sizes that all of your vendors can build, and design your boards to fit in those panels. Fabrication panel must accommodate these. There are things that have to go in that panel besides the circuit boards. They have to accommodate the boards themselves. We just talked about that. There have to be tooling holes in the panel. The panels get drilled, plated, etched, imaged. These things all happen in different machines. So they have to pick the panel up, move it to another machine, and when they put it down and line it up, it better be nearly perfect. The alignment better be within a few 10,000ths of an inch, or good luck, you're not going to get alignment of these processes. So they have to have very tight, accurate tooling holes in them to be able to move from station to station. They need an outer perimeter area for thief copper. Thief copper? I will explain thief copper in a short while, and it'll make perfect sense. But for now, take my word for it. They must have an outer edge of the panel with thief copper in it, or they can't produce your board accurately. Understand that? We'll explain why in a minute. They need a routable area between the boards. And based on these next two bullet items, they also need to be able to put coupons in the board, microsectioning and etch coupons in the board, as well as impedance coupons if you're doing impedance controlled design. They don't test the impedance on the board itself. They test it in the panel that contains the boards. They look at microsectioning coupons from the panel, knowing that the boards themselves will pretty much match that microsection look, and how well the holes are plated, how well they're drilled, how well things are imaged and etched, and so on. They can tell all of these things from the coupons. We'll talk more about that as we go. All of these things need to fit into that panel, all with minimum scrap. The less scrap you have, the lower cost your boards will be. And if you don't design them right, you put yourself in harm's way. When I first went to L3 Avionics, I'm sorry, not L3, Goodrich Aerospace in 1990, I was talking to the mechanical engineer in the company, and he said to me, Rick, you're going to be working with me on an upcoming project called TCAS, Tactical Collision Avoidance. Anybody who's a pilot knows what that is. We had landed a contract with the Navy to equip X number of the Navy's planes on a trial basis with TCAS. And Wade, the mechanical guy, said to me, he said, we know where the equipment bay is in the aircraft. We know how big our box is going to be in that equipment bay. And based on the box size and the area we have inside, we know that the circuit boards that are going to plug into the backplane can be anywhere from 5 to 7 inches wide and can be anywhere from 11 to 13 inches long. He said, I recently found out that fabricators build 18 by 24 panels. And so based on that, I thought, oh, perfect. Let's pick a board size that maximizes yield in this 18 by 24 panel. So I made the boards 6 by 12 to fit into this 18 by 24 panel. Well, that's all fine and dandy, except unfortunately, what he wasn't aware of is you don't get the whole panel. As I said a minute ago, there are other things that have to go in the panel. most of all, there has to be a thief area around the edge. I checked with the fabricators that Goodrich was using at that time, and I found out that all of them required 3/4 of an inch band all the way around. Meant they were going to lose 1.5 inches off of the 24-inch side and 1.5 inches off of the 18-inch side. So the usable area that was left was 16.5 by 22.5. And the circuit boards all had to fit into that area. Well, unfortunately, 6 by 12-inch boards can only fit a few boards into here. He was hoping to get 6 boards per panel, and that was his goal with this 6 by 12. But the sad reality is only 3 boards of that size would fit in that panel. And it meant that a lot of the panel would be wasted. All the material outside of the area of those boards was going to get thrown in the scrap pile. And they were going to charge us based on how many boards we bought and how many panels they had to run. So if we bought 300 boards, for example, they'd have to run 100 panels or more, 100, 101, 102, 105, depending on just how well we designed our boards. And that's what they would charge us for these boards. The time we were buying these, we were buying fairly low quantities at the time because we were doing pilot production and early production runs. And we were paying about $150 per panel for 6 and 8 layer boards. That was our typical cost per panel in these boards. At that cost, with 3 boards per panel, they charged us $50 a board because they could only get 3 boards in a panel. So I said to the mechanical guy, if we could change the size of this board and just reduce it slightly, we'd take 4/10 of an inch off the entire perimeter of the board, reducing the size to 5.2 by 11.2. Could we fit all the components in? We checked with the double E's. Yes, we could fit the components. Could we route stuff comfortably? Yes, we could route stuff comfortably. We could get the connectors to plug into the backplane. We could get everything we needed into this board size. And the beauty of this board size is it would allow us, as you can see in the picture, to put 6 boards in the space that we had available. And not only would there be 6 boards in that space, there would be area for thief copper around those boards. Again, I will explain thief copper in a short while. And the end result is that with 6 boards per panel, that also left us, pardon me, room for coupons in the panel between the boards and a routable area between the boards themselves, and reduce the cost per board to $25 a board. The cost of the board was cut in half, by changing the board size by 4/10 of an inch all the way around, 8/10 of an inch on each of the major dimensions. The boards have still worked perfectly and were half the price. If IBM had actually thought about the motherboard, and clearly they didn't, and had made it, instead of 12 by 13.8, had made it 11 by 15, the components that they put on that motherboard would have fit. They could have routed the board, and they still could have mounted that board into the case that they were planning. They wouldn't even have had to have changed the case size for the XT. It would have fit in that case. And their price per boards would have cut in half. Because now, at 11 inches wide, they could have put 2 11 inches in that 22.5 inch available space inside the thief copper, and could have gotten 2 boards per panel instead of 1. Their board would have been half the price. Now, as it turned out, IBM won anyway, because they are so large and they made so many of these that the market changed to meet them. The industry changed to meet IBM instead of the other way around. But had the PC only become a normal selling piece of equipment, not a phenomenon, it became a phenomenon, as everybody knows. But had it just been a normal piece of equipment where they were producing at most a few thousand a week, I can tell you with clarity, fab shops wouldn't have spent millions of dollars to re-equip themselves just to satisfy IBM's needs. The only reason they did it is because they saw quantities large enough to justify it. These things don't happen for the heck of it. They happen because they need to. So Understand, when you design, unless you're an IBM sized company and truly believe that your product is going to dominate the marketplace, when you design it, make sure you design it to fit into the processes that the fabricator uses, into their panels and into their processes. Understand that. Also, oh yeah, don't forget about assembly rails. If you push components all the way out to the edge of these these boards, the assembler still has to grip the edge of the board to produce it. And if you've got components going all the way out to the edges, they have no place to grip. That means you have to attach 1/4 inch, 1/2 inch, 3/4 inch, whatever they demand, assembly rails on the edge of this. And all of a sudden, you're no longer going to get 6 boards in the panel. You're only going to get 4 boards of this size in the panel if you have to add assembly rails. And the cost is going to go back up by 50%. You have to know these things and think of these things when you're making the decision. If you're doing very small boards, as shown in this picture here, you may, the assembler, the CM, whether they're in your house or a contract company, may ask you to put 2 or 3 or 4 or however many boards into an assembly panel. And they'll give you the sizes that they like to use. This is an assembly panel I've used before for small boards. And a lot of the small boards that we did at L3 would fit nicely 3 up in this 7.5 by 8.5 assembly panel. And the beauty of this guy is it would fit 6 up into an 18 by 24 panel with room between them to route them out. And we would simply put V-grooves or mouse bites around the circuit boards inside the assembly panel. And all this worked perfectly. And as I said, it fit perfectly in the 18 by 24 panel. But Rick, you've got the panels, the assembly panels extending into the thief copper area. Yes, I do. Notice the PC boards themselves do not extend into the thief copper area. The assembly pallet or assembly panel can have thief copper on it because it'll overplate. Thief copper overplates, and you'll see why in a short while. It can overplate and have thief copper on it because it's going to get torn off and thrown away. So when you have to build things into assembly pallets, you can do this, but don't let your board extend into the thief area. Understand the processes. Work with the fabricators. Let's go through quickly how circuit boards are produced. Talk a little bit about how a 4-layer board is manufactured. When you send a artwork to a 4-layer board shop, they're going to start with a centered core of material. A lot of people think they will take 2 cores, print and etch, and laminate them together. That's not how it works. If you want to do it cost effectively, they will do what's called foil lamination. And to do that, they will start with this center core that you see in this slide. And the center core will be fully polymerized, cured to the C stage, meaning that it will never go to a liquid state when you put it under high temperature and high pressure in a laminate press. It's fully polymerized. And on either side of it is a sheet of copper foil. And also one thing to notice about this particular picture, it is inaccurate in the sense that when you're building a 4-layer board, that center core will actually be about 25 times thicker than either of the sheets of copper above and below it. This is just a drawing, and the guy who drew it, Dan, the guy who drew it just to get the point across how boards are fabricated. His intent wasn't to accurately depict the process. In a 4-layer board, that center dielectric will be much thicker than the copper, but this is what they will start with. The next step that they will do is to place what's called an etch resist on the surface. It's typically a blue plastic material like you see in this upper left picture on the slide. They add that to the thing. After they have imaged and removed, they will remove the etch resist in the areas where they want to remove copper. They then put it into an etching tank, and that etches away the copper in the open areas of the etch resist. They then strip away the blue material. And when they're done, they get what you see in the lower right picture here. They get that center core with all of the copper printed and etched, and they will then neutralize the acid from the etch. They'll do a thorough cleaning. They'll do a DI water rinse, as well as other steps. And then they do what's called a treatment, an oxide or film treatment to the copper surface. Why do they give it a treatment? Because they need to form a tooth, a small tooth. They need for it to have a little bit of a jagged edge across that entire surface of copper. Why? So that the material we're going to laminate to it will adhere well. If this copper's too smooth, the material we add to it won't adhere well. After this is done, they will lay it up as shown in slide 12 in a laminate press along with plies of prepreg material, and they'll put a sheet of copper foil above and below all of that. What is prepreg? Prepreg is the same material as that which is in the center of the core, except it has not been fully cured or fully polymerized. It's only been cured to the B stage, meaning when you put it in a laminate press under heat and pressure, it'll go to a high viscosity liquid state. It'll go to a syrupy state where it'll flow like a thick liquid. And the idea is to fill in all the valleys where we've removed copper on the center core. And at the same time, have that prepreg adhere to the sheets of copper foil that we put on top and bottom of the stack up. They put it in the press, pressure temperature for a given amount of time. Over time, the prepreg cures to the C stage, at which time the core is fully cured. The entire stack has been fully cured, and we now have what you see in slide 13 in the upper left. We have a fully, completely cured 4-layer stack up with all of the interlayer copper printed and etched. The next thing they do, as already seen in this picture, is they drill holes. Wait a minute, Rick, they drill holes before they image the traces and pads? Absolutely. The next thing they do is drill the holes. They also will do what's called smear removal in these holes. When you push a drill bit down through this circuit board and it encounters the epoxy and fiberglass, the fiberglass is really, really tough stuff, and it heats up the drill bit. These are diamond tip drill bits, but they still heat up from the friction caused by the fiberglass. The drill bit gets hot as it pushes through the epoxy, it melts some of it, and when you pull the drill bit back out, it pulls epoxy along the whole wall and creates a smear, as it's called, along that whole wall. If we attempted to plate the holes in the board at this point in time, the plating would not stick to the inner layers because there is an insulator covering those inner layers, the epoxy smear. So the next thing they have to do is what's called a de-smear or etch back process, where they attack that smear with an aggressive chemical to eat that smear out of the hole. Now, once that has been done, they then add, as you can see in the bottom right, a thin layer of copper. It's chemically deposited on the walls of the holes in this panel. Now, this thin copper layer also gets added to the surface copper. They don't really care about that. They don't need it on the surface copper, but it doesn't matter that it gets added there as well. Where they really need it is in the holes. Why? Because they need the surfaces and the whole wall to be fully conductive so they can electroplate the copper in the whole wall. You can't electroplate unless you have a conductive surface. And that's why they make this conductive, so that they can have a fully conductive surface all over and through the holes. Sometimes they use what's called a carbon deposition. Whether they're using electrolysis or carbon, either way, this deposited material is only a few microns thick. A micron is a thousandth of a million. It's a millionth of a meter. I couldn't think of the right way to say it. It's a millionth of a meter, so it's a really thin. A thousandth of an inch is 25 microns, to give you another perspective. What the people in the US refer to as a mil, a thousandth of an inch, is 25 microns. This material is only a few microns thick, very, very thin material. In the old days, before the days of what's called I'll think of it in a minute. In the days gone by, they used to do what's called, it was called pattern plating. Pattern plating is what we do today to plate the extra copper on the board. Back in time, in the early days of fabrication, they would do what's called panel plating. They would take this panel just as you see it in this lower right picture, and they would put it into a plating tank as shown on slide 14 in the upper left. Now, this is a cartoon that I got off the internet just to show how electroplating works. I didn't want to show a circuit board house plating tank. I wanted you to really understand the process, not what the plating tank looks like. Imagine that this circular object is the panel that we just put electroless copper onto. If they put that into this tank and attach the negative electrode from a power supply to it, a DC power supply, and attach the positive side of the power supply to a copper anode that's in the plating bath, and they had a copper sulfate solution in the plating bath, as current, I should say, as energy moved from the anode to the cathode is now our circuit board panel, as energy moved from the anode to the cathode through the plating bath, it would carry copper in the solution to the panel that we're trying to plate. And over time, we would plate copper all over that panel. And that's how it used to be done. That's called panel plating. And I'll tell you in a few minutes why they don't do that anymore. They now do what's called pattern plating, and I'll explain pattern plating in just 1 second. But anyway, this is how electroplating works. The fields move through that bath evenly from the anode to that. They're attracted by that entire 18 by 24 panel. They're attracted to that entire panel, and copper wants to plate evenly all over that panel. And again, we'll talk about why in a minute. Today, they do what's called pattern plating, as shown in this lower right image on slide 14. They will put a material on that panel that we have just put electroless copper in the holes. They'll put a material called a plating resist. Why? Because they don't want copper to plate everywhere. If you plate copper everywhere, then you have to etch through the base copper and the plated copper when you want to etch traces and pads. Unfortunately, we make images today that are so small, it's hard to plate through copper that thick and still be able to produce narrow traces. And that's why they don't panel plate anymore. They now pattern plate. So they put this plating resist material on, and they then drop it into the plating tank, as you see in the upper left picture. And if our circuit board, imagine our circuit board looked like the right side image on slide 15, as you can see it here. If I designed a circuit board like this and sent it to a fab house, the fab house would immediately call me up and they would say, Rick, what are you thinking? We can't build this board. And I would say naively, why can't you build this board? And they would say, because this board has uneven copper all over it. We can't plate it evenly because you haven't distributed copper evenly. Remember, we're going to put, let's say, 6 or 8 of these into an 18 by 24 panel. Let's say we're going to put 8 of them in a panel. When they drop that panel into that plating tank we just looked at, the fields from the copper anode conducting to the panel are going to attempt to couple evenly all over this entire panel. Why? Because there's copper underneath the plating resist. Imagine that this black material is plating resist. And underneath that is a solid sheet of copper. and the fields will be attracted all over this panel to that solid sheet of copper. So the fields are trying to plate copper evenly all over this panel. But unfortunately, when the energy gets to the panel, we don't have an even distribution of copper. And what would happen if they tried to build this board as you see it, the upper area would tremendously underplate because the amount of energy coupling to it would get spread out across a lot of copper. And the bottom area, where there's only a few copper features, the energy and the solution that would be carried to that area would only be spread out over a very few features. The bottom would tremendously overplate. Lines would overplate, holes would overplate. And if we left it like this, we would probably also end up with holes that were shaped like ice cream cones. They wouldn't be cylinders like we want. They would be conical in shape. Conical shaped holes have uneven knees, and uneven knees are too thick on one side and too thin on the other, and they're prone to failure. This kind of board would be extremely prone to failure and would cause major reliability problems. So they're going to call me up and they're going to say, Rick, we can't produce this board. What are you thinking, man? And I'm going to say to them, what do you need to do to produce it? And they're going to say, well, we need to even out the copper on this board. Oh, how are you going to do that? And they would say to me, we're going to put thief copper on this board so that we can create even copper plating all over this board. Oh, so what are you going to do? We're going to put thief dots in the area where you only have a few traces. We're going to fill that area up with dots of copper. And most people say to them, yeah, that's okay. Go ahead and do that. You know what's wrong with that? Those thief dots will attract fields. Oh, Rick, they aren't attached to anything. They won't attract fields. Want to bet? You do not have to have something attached to, you do not have to have copper attached to anything for the fields in the dielectric to be attached, to be attracted to them. The energy in a circuit moves in the fields, not in the voltage and current. And when the fields move through the dielectric below those thief dots, they will couple energy into those thief dots, as seen in this picture. If you had thief dots in this board, the fields in the dielectric under it would create current flow in those thief dots. And that would in turn create a magnetic field. And the fields would then potentially couple into other circuits on the board. Is that what you want to happen? To have unattached copper coupling fields into places where you don't want them? Well, of course not. So when they call you and say, hey, we need thief copper, you say, no, I'll fix the problem. Don't let them fix the problem. You fix the problem. Trust me when I tell you. They could not build this board unless someone fixed the problem. Either they're going to have to add thief copper, or I'm going to have to do something else to the design. Because as you see it, they cannot produce it properly. Can't be done. So it's up to me in this case to fix this problem. What I should do is add copper pour all over the bottom area of this board, the bottom half of it, and attach it to something, to ground, to power, to something, so that the copper is balanced, so the copper will plate evenly in and on the board. And you need for it to be balanced on both the top and bottom of the board, not just all over each surface. Copper needs to be balanced all over the outer surfaces, and not only the outer surfaces. Unless you want your circuit boards to be warped and twisted and look like a potato chip, you need copper evenly distributed all over the inner surfaces. You should be adding copper pour to every surface of your boards. And if you want to know how to attach them properly, attend one of Lee Ritchie's classes on power delivery, or attend one of mine on power delivery, and we'll tell you how to properly attach that copper so that it does its job as it's supposed to. A lot of people think pouring copper on the surface of a board is an automatic cure for EMI. Not true. It may help, but it may not. You have to attach it to the right voltage or ground depending on the other layer. So the point is, know what you're doing, pour copper all over the board and attach it to something. Don't leave it uneven. And oh, by the way, the reason they need thief copper around the outer perimeter, imagine the top edge of this board is one of the boards at the outer edge of the panel. If there was no thief copper outside of these boards, the entire edge of that board, about a ½ inch in, would overplate. Because again, the fields are drawn to that area and they need to have even plating. They put thief copper there so the thief copper will overplate because they're going to throw it away. They don't care if the thief copper overplates. They don't want your board to overplate. That's why they need thief copper on the outer edge of the panel. Design the board so it's balanced. Anyway, getting back to this picture, they have added plating resist, and we've got a balanced panel, right? Because you've put copper everywhere, or in this case, I've put copper everywhere to balance the board. So they then put it into a plating tank, and they will end up with the board as you see it in this lower right image on slide 16. They will end up with a board that has plating on all the outer layer features and in the hole. And in the hole. That's the key here. They have plating both on the surface and in the hole, and that's the secret to success in this particular case. After that, they will, as shown on slide 17, put a thin layer of tin or tin lead on the plated copper. I don't want tin lead on my board. They're not going to leave it there. They're putting it there for a reason. They will then strip away the plating resist that they had on the board, leaving what you see in the lower right picture on slide 17. And they would then put it into an etching tank and etch away all the copper except the copper that's underneath the tin or tin lead. Oh, that's the reason for the tin or tin lead. It's an etch resist, exactly. That's why they put it on there. Some fabricators don't use tin or tin lead, they use something else. The point is they put something on there as an etch resist. And then as shown in the bottom right of slide 18, they strip off the the etch resist, and they now have a fully finished board other than the few final finishes that go on it. As shown in the upper left of slide 19, they would add a solder mask to the board if you're doing solder mask over bare copper. And then as shown in the lower right of slide 19, they would then put some kind of finish on the features that show in the board. Electroless nickel immersion gold, which is ENIG. And oh, by the way, I think I might have mentioned this talking about Happy's report card. Unless you need ENIG on the board because of needing really flat pads, you shouldn't be using it. It's one of the most expensive finishes there is. If you only have medium density surface mount components, meaning medium, if you don't need really, really flat pads because of very fine pitch parts, you don't need ENIG. Use something like immersion tin or immersion silver, or maybe even an OSP finish, which is an organic finish. Only use ENIG if your assembler tells you, yes, you absolutely need it, because it's more expensive. It will add cost. Anyway, final finish, and then the board is completely done. I mentioned coupons in the circuit board itself. Imagine, if you will, as shown in slide 20, that they, in that coupon area of the panel, used, once they had extracted the boards, they're going to route all the boards out of the panel, and now they've got the leftover panel material. They will take the area where they put the coupons, and they will cut out a coupon like you see in the upper picture on slide 20. And they will then cut through the center of the holes with a very sharp saw so they don't create burrs on the copper. They will then clean that very well and buff it, and then put it in a dish and fill the dish with epoxy. Let the epoxy fully cure. Then they take that round slug out of the dish, and those holes are now up against one edge. They buff that edge where the holes are until it is smoother than a baby's bottom. I mean, they buff this thing until it is just perfect. And they then put it under a microscope and look at it at 100 or 200x magnification, as shown in the picture on the right side of slide 20. What you see in that is that cross-section of a hole. They can tell so much from this coupon. It is unbelievable. They can tell just how well the hole was drilled. If the drills were dull, how can they tell if it was dull? One, they're going to get tearing of the fiberglass at the edge of the hole. And two, notice the inner layer copper where it comes up to the edge of the hole. Notice that that copper has a little bit of a look of a nail head. It's got an elongation to it right at the edge that makes it look a little bit like a nail head. That's called nail heading. And when they see nail heading start to become extreme, they know, aha, our drill bits are dull or becoming dull and need to be taken out and sharpened or replaced if they've been sharpened more than a few times. They will only sharpen drill bits so many times and then they pitch them, because they can only do so many sharpenings before the drill bit becomes useless. Drill bits are very expensive, one of the most expensive operations in a fab house. And if you're going to fab houses that charge you a low price, there's a good probability that they're pushing their drill bits beyond normal usable life. I could tell you stories for days about that. I mean, I have so many stories about dull drills and failed equipment in the field because our company bought boards from the cheapest vendor. I could tell you stories forever about dull drill bits. Know what you are getting. By the way, every fabricator will put coupons in the panel. Tell them you want these coupons shipped to you. And you want evidence that the coupon came out of the panel that made your boards. Don't let them send you someone else's coupon. Make sure they're your coupons. You want certified proof that that's a coupon from the panel that made your boards, because you want to look at them. You can tell if they've pushed drill life. You can tell if they haven't done an adequate job of desmear. You can tell if plating is even and if it's the right thickness. Plating on the whole wall should be between 0.8 of a mil to 1.4 mils. Ideally, it should be 1 to 1.2 mils on the whole wall. And that has to do with long-term reliability. I'm not going to get into that now. It's all in the IPC standards. That's what they will build to, because that's what you need to design to. Understand these things. Ask for the coupons. Examine them. Utilize their benefit. Anyway, they can tell so much from these coupons. It's remarkable. Learn that. If you don't know these things, do your own studying. Figure out the advantages and the value of coupons. And then request the coupons and look at them yourself. Etching will reduce traces on inner layers, by about 1.5 mils when you're using 1 ounce copper. Which means what? Which means they're going to take your artwork. If you're asking for a 4 mil trace and it's 1 ounce copper, they're going to increase that trace to 5.5 mils if it's on an inner layer. So when they etch, it'll etch back to 4 mils. Oh, shouldn't I be doing that? We'll talk about that in a minute. On outer layers, it's going to reduce the copper on the edges by 1 mil on each side, or about 2 mils overall. So a 4 mil trace will get widened to 6 mils. What does that mean? That means if you're asking for traces that are too close together, like 2 mil lines with 2 mil spaces, there's a high likelihood they can't produce them. And oh, by the way, if you're asking for 2 mil lines and 2 mil spaces on a 4 or 6 layer board on the outer layers, there's a high probability they can't produce them at all without changing copper weights. And if they have to go to a really thin base copper weight to be able to produce your 2 mil lines on the outer layers of that 4 or 6 layer board, you will pay extra for that. That's a special order. They're not going to be using standard materials, which means, they can't build what you've asked without a special build, and you will pay extra for it. The point is, don't put 2 mil lines and spaces or even 3 mil lines and spaces on the outer layers of 2, 4, and 6 layer boards when they're using standard copper weights because they can't produce it effectively. Know what can be done. Talk to the fabricator. Drink in their knowledge. Ask them the questions. What can you do and what can't you do? Can I do this? Can I do that? We're going to talk more about that in a minute. Multi-layer pressing will cause what's called resin gathering in areas where there aren't a lot of traces. And those areas are called resin-rich areas. Resin has a dielectric constant of about 3, and fiberglass has a dielectric constant of about 6. So when you get a lot of resin in an area, that will lower the dielectric constant for the traces in that area by as much as 0.5 point. Well, what does that do? When you change the dielectric constant, the traces see, it will, in this case, you're lowering the decay, it will raise the impedance. What? Yes, it will raise the impedance of the traces. Well, shouldn't I compensate for that? No. Don't ever, as this bottom note says on this slide, don't ever compensate for the fabricator's needs. Make sure you design so they can produce your board. Don't put 2 mil lines and spaces on the outer layers of 2, 4, and 6 layer boards unless you're prepared to pay a lot more for them, because that's not producible. Know what they can and can't produce and design around their absolute needs, and then send them the design and leave them alone. I had worked with an engineer once in a major company who loved making lines bigger so that we could compensate for etch factor. Oh my God. It took me forever to drive into this guy's head. We don't want to do this. We want to leave the fabricators alone and let them do their job. They know what they're doing. Don't tamper in their field. Stay out of their business. Let them do their job. Never ask a fabricator what is the smallest hole or trace or space or feature that you can make. I mean, you want to know that, but don't ask that only. What you should ask instead is, what's the smallest hole or line that you can make without a cost adder? Ask them, if I make 1/10-inch wide lines and 1/4-inch diameter holes, and I start reducing those holes in diameter and start making those 1/10-inch lines narrower, at what point is the price going to go up? And by the way, they're going to give you different numbers for different types of boards. They'll give you different numbers on inner layers than outer layers. They'll give you different numbers on 2, 4, and 6 layer boards than they will on 8, 10, 12, and so on layer boards going up, because they'll use different copper weights. Oh, I see. Yes. Where is there a break point? And then you ask the next question. If I keep making them smaller still, where's the next plateau? Once you know these plateau levels, stay above them as much as you can. Once you know the maximum trace width or the minimum trace width they can produce at virtually no cost adder, make your traces that wide when you can. I mean, if you have controlled impedance and can't do it, well, then you can't do it. But if you're not doing controlled impedance work, make your traces that wide if you have room for it. I've met people who will put 4 and 5 mil lines on circuit boards where they only have 20 or 30 traces. Think about the images that were on that picture that I showed you when we were talking about plating. The image from Euro Circuits back on, I forget which slide it was. Think about that image, how uneven that copper was. One of the things the designer could have done is make the traces much wider in the area where there was no copper pour. Why not? Think about it. People don't think about, I've seen people put 4 mil traces when they only have 20 or 30 traces on a surface of a board. What are they thinking? Again, if it's impedance controlled, yes, then you have to. But if it's not, don't do that. Once you know the answer, never go below that width unless you have to. And when you have to, minimize the usage. This last bullet item on slide 22 shows an example of the last time I asked a fabricator, and it's been a while, so the numbers may be different now. The last time I asked, What's the minimum trace you can produce without a cost adder? They said 6 mil lines. And what's the minimum hole size, a plated hole, that you can produce without a cost adder? They said 13 mils, finished hole or larger. Talk to your fabricator, ask those questions. Don't assume. And go above those sizes when you can. Make their job as easy as possible. If you have to have 2 mil lines in the area of a 0.65 millimeter pitch BGA so that you can get some of the lines out of the pin field, then use them, but only use them there. Don't use them everywhere. Understand the impact you have on design. Talking about slide 23 for a minute, things you need to know or things you need to ask. What IPC class are you designing to? Well, what is IPC class? By the IPC standards and you'll know. It's a producibility level. If you're building toys or appliances, you're probably IPC class 1, which is a very producible class. It's easy to produce class 1 because their potential failure isn't oh my God if it fails. If you're building medical equipment that absolutely can't fail, or military equipment that absolutely cannot fail, fail-safe equipment, then it might be class 3. If you're almost anything else in the world, you're probably class 2. When I was at L3, we designed and built avionics equipment. Some of our avionics equipment was for the military, and some of that was class 3. The majority of what we produced, including some of the military gear, was class 2, meaning it could fail without the world falling apart because there were backups within the equipment or backup equipment to take over for it should it fail. Most equipment in the world is class 2. If you're going to design to class 2, don't ask them to build to class 3. And don't design to class 3 and then only ask them to build to class 2 because you'll be over designing the board. You'll be doing more than you have to, and you'll be just constraining yourself unnecessarily. Understand the needs, design around them. What are the pad to hole ratios that your fabricator can live with? What's the hole? This is a very important one. We talked about it earlier. Hole to board thickness aspect ratio. What is the hole to board thickness ratio they can live with, and where does a premium start to kick in? And where does it get so small they can no longer do it? You need to know all of those numbers and live within the numbers. What's the minimum line width? What's the minimum space, feature spacing? What's the plane to hole clearance? If you have power and ground planes in the board and put an anti-pad, an open hole in the plane that you're going to have your drilled holes go through, what is the minimum clearance from the edge of that hole to the plane? And it's probably going to be bigger than you think. Talk to the fabricators. I mean, if you're doing, for example, 10 mil plated holes in a 62 mil thick board, they probably had to drill a 12 to 13 mil hole before plating. And they probably need 8 mils all the way around in the anti-pad. So that's 16 mils plus 13. They need a 29 mil diameter anti-pad in the plane for that 10 mil drilled and plated hole. What? Very likely. Again, I may be living in the past. Maybe 8 mils is bigger than they need. The point is, ask the question. You have to know. You can't assume that what you're doing is producible. Think about it. Do they need silk screen? Do they need solder mask? You know, what text size do they need minimum for silk screen in case you're forced to use really small characters and letters? Know what the art of the possible is. Live within their needs. When doing 2.5 and 3 mil lines, I mentioned this a moment ago, only use them where you need, and make sure that you only put them on outer layers if you're willing to pay an extra cost for low layer count boards. You can put them on outer layers of high layer count boards because they're going to use thinner copper anyway. But if they're forced to go to 1/4 ounce copper instead of 1/2 ounce copper on your 8, 10, 12 layer board, then you're still going to pay a premium. Whenever you do these things, you probably incur a premium. Know that, understand that, live with it. Minimize the use of these features. When routing, never space 2.5 and 3 mil lines apart by 2.5 to 3 mils. Because remember, they have to make it wider to etch it back. And if they get the 2 mil lines, say, let's say they make them 3 mils wide in order to produce them, and you've got them separated by 2 mils, you have so little area between them, they can't put a plating resist between them without it flaking off, which means you're going to get shorts between those 2 mil lines. Know, recognize the needs that they have to have, and live with them. When a PCB is 2, 4, or 6 layers utilizing standard copper weight, do not use 2.5 to 3 mil lines. Understand the needs. Always use the widest line that the design allows. When you have imbalanced copper, like in this design, fill that area in with something. Don't leave it open. Either make the lines wider or fill it in with copper fill of some kind. Don't allow unattached copper in that area. We talked about that earlier. Use the largest via hole that spacing allows. Good design rules for vias. Only use via and pad when nothing else will do. It makes repair and assembly harder. So do it only when you need to. Only use blind or buried HDI vias when you have no other choice because of feature size or pin pitch of BGAs or whatever, or when it can reduce cost. If you're doing 40 and 50 layer boards, as some people do, you may be able to actually lower cost by going to HDI. Look into it. Understand the needs, the wants, and so on. Non-filled vias need an opening around the via hole, not around the pad, just around the hole. Why? Because if you try to put solder mask over a non-filled hole and you're using LPI mask, the mask material will collapse into the hole, and when the mask is cured, you will trap chemicals in that hole that can potentially cause board failure over time. Understand the impact that you have on the design. Vias properly sized can be assembly test points. We used to use vias, and on certain areas of the board where we had room, we would make the pad on one side of the board or the other a 35 or 40 mil square pad with a nice big opening, solder mask opening around the pad. We did that so we had test points for vias. I mean, if you've got a via there anyway, make it a test point if it's in an open area of the board. Why not? We did this a lot. 100% test point coverage on circuit boards is absolutely mandatory if you expect them to be able to ship you boards that they can guarantee will come up every time you fire them up. If you can't give 100% test coverage, they can't guarantee that they're going to be able to supply you boards that work perfectly every time. Assemblers need full coverage to do full in-circuit testing. We used to spend weeks after prototyping putting test points in really high-density boards at L3 because we knew that before we shipped that thing for final production runs that we needed to have 100% test point coverage. If you can't do that, well, I'm sorry. You can't be guaranteed it's going to function. Is it costly? Oh, man, is it costly to design those in? Do you want them to be producible or not? You have to decide. HDI Microvia Technology should only be applied when you can do it cost effectively. This is a cost effective, this picture on slide 27 is a cost effective HDI design because they're going to build a thin 4-layer board, print, plate, etch, everything just like they would any other 4-layer. Then they'll add a layer of laminate top and bottom. They'll blade the via wells and then they'll plate all the copper on the surfaces and in those vias after everything has been ablated. This is an inexpensive way to do this. If, as the bottom note on this slide says, if you have to add through vias after you put the HDI vias on, that's going to add cost. That will make it more expensive. Try to use all HDI vias from layer 1 to 2 and have all your through vias from layer 2 to, in this case, layer 5, so that you don't have to pay extra for through drilled vias. This is something on this next slide, 28, that we did at Goodrich Aerospace in the early 90s with a lot of our RF circuits. We would do blind depth drilling from layer 1 to 2 and from the bottom layer up to the next layer above, so that when we drilled all the through vias, they could do blind depth drilling to the blind vias, and then they would wash plating solution into these via wells at the same time they plated the through holes. And this worked extremely well. This gave us very good process control and very inexpensively. There was almost no cost adder to do this versus a standard through hole board. When you have to use HDI vias, this next slide shown on slide 29 is a perfect example of what not to do. I mean, if you're going to drill the center core and then plate and etch, that's plate and plate, etch and plate that center core, and then turn around and add 2 layers of via material to do 2 different blind buried via layers, and then put through holes on top of it into this, oh man, are you asking for an expensive board? This will be, the fact that you can connect any layer to any other layer doesn't mean you should. Having drilled holes after the HDI buildup layers really adds cost, as noted in the bottom bullet item on this slide. This is an expensive board. Don't go there unless you must. This is what people used to do in the days of blind and buried vias before there were HDI or blind depth drilling. This is called sequential lamination. They would build, for example, if you needed an 8-layer board, they'd build a thin 4-layer center core, and they'd do all the printing, plating, etching, blah, blah, just like any other 4-layer board. They would also make 2 fully built 2-layer boards with plated holes, one for the top and one for the bottom. So far, they've made 3 circuit boards. Then they'll laminate these together and then drill the through holes all the way through all of these layers and plate all of that. You can only imagine what this cost. And there are people today still doing this. This is called sequential lamination. It's a very expensive way to produce a bare circuit board, and there are people today still doing this. Avoid it unless you absolutely must. This is very reliable, and there are some military suppliers that still do this, but don't do it unless you really need to. Get to know the person in your fab shop that knows all the processes. Get to know the person who knows all these bullet items talked about here. Impedance control, some knowledge of electronics, artwork layout, mechanical processes, chemical processes, testing, test coupons. Talk to the person it's probably someone in engineering that understands these processes well. Get to know the person that knows the fab processes and the impact they have on panel sizes that your fabricator will use, their preferred structure for each board stack up, the impact of copper balance on plating and warp and twist, aspect ratios, land to hole, minimum no cost adder line widths. You need to know answers to all these questions. You need to know the person at the fabricator that can answer these questions for you. Talking about assemblies for just a minute. Get to know the person at the assembly shop, the CM, who can tell you how to best process your board. Try to figure out ways to have 1 IR reflow process if possible. 2 IR reflows means it's going to cost more and you're going to subject the board to more heat. When you subject the board to more heat, you're going to be challenging the long-term reliability of the board because you're stressing it more than you absolutely need to. If you suddenly realize, oh, we not only need 2 IR reflow processes, we need to expose it to wave solder processing because we have through-hole components in the board. Now you've exposed it to 3 heating processes, and you've exposed some of the components to more than 1 heating process. which means you're going to shorten their life. This slide, this bullet list on slide 33 comes from Happy's paper. Take a hard look at it. Read Happy's paper. Go to Altium's website, download this paper. It has all of these bullet items in it and talks about their importance and what you need to know about them. This picture on slide 34 and the one on slide 35 are also in Happy's paper. Get to know all of this stuff and get to know it well, and get to know the impact you have on fab and on assembly, and know the breakdown that you will create at the fab and assembly house and the cost impact that you have. You need to know those processes inside out. If you don't, you're compromising the overall quality of your circuit boards if you don't know these processes inside and out. Know them, respect them, know what to do to minimize thermal stresses at the assembler, stresses on components, fab processes, all of these things. Know how to design to minimize those effects. Thank you so much for your time.